Welcome to The Explainer. Today, we're diving into what might just be the single most important paper in all of modern AI. Seriously, this thing is the spark that lit the fuse on the AI explosion that we are all living through right now. Let's break down the paper that really started it all. Attention is all you need.
So, back in 2017, a team of researchers at Google publishes this paper with this incredibly bold, almost cocky title. It was making a huge promise. And, as we're about to see, it delivered in a way that completely reshaped, well, everything.
And I'm not exaggerating here. The main idea in this paper, this thing called the transformer architecture, it is the fundamental blueprint for almost every single major AI tool you use. We're talking ChatGPT, we're talking advanced code generators. This is the origin story.
Okay, so what big problem were they even trying to solve? Well, it really boiled down to a fundamental speed limit in how AI could process language. You can kind of think of it as a reading problem, but on a massive, massive scale. See, before this paper, the models that dominated AI had to process language sequentially, one word at a time, in order. It's like trying to understand a whole page of a book by looking at it through a tiny little straw. Sure, you can do it, but man, it's slow, and you're probably going to forget the beginning of the sentence by the time you get to the end. These older models were called recurrent neural networks, or RNNs for short. And the way they worked was by passing a little bit of memory from one step to the next. So to understand word number 10, the model needed its memory from word 9, which needed its memory from word 8, and so on all the way back to the very first word. And you can see how this created a huge bottleneck, right? First off, it was just slow. You couldn't process all the words at once. You had to wait for the one before it to finish. But more importantly, it made it incredibly hard to connect ideas that were far apart. That little bit of memory, that signal, it would just get weaker and weaker over a long paragraph. And this is where the big breakthrough happens. The researchers asked this totally revolutionary question. What if we just got rid of that whole step-by-step process? What if a model could just look at the entire sentence at once and figure out for itself which words matter most to all the other words? They called this brilliant idea self-attention. And what it is a mechanism that lets the model, for any single word, look directly at every other word in the sentence and give it an important score. It builds this rich web of connections between all the words, all at the same time. Now here is the real genius of it. In those old RNNs, the computational path from the first word in a paragraph to the last word could be hundreds and hundreds of steps long. With self-attention, the path length is always one. The first word and the last word are direct neighbors. This just completely vaporized the problem of understanding long-range connections. Okay, so self-attention is the big, powerful idea. But how do you actually build a machine around it? Well, that machine is called the transformer. Let's pop the hood and take a look inside. So from a 30,000-foot view, the transformer has two main parts. You've got an encoder, which reads and understands all the input text, like, say, an English sentence you want to translate. And then you have a decoder, which takes that understanding and generates the output, like the translated sentence in German. Now, this basic structure wasn't totally new, but what they put inside was the game changer. The engine at the heart of this thing is called multi-head attention. So instead of just having one self-attention mechanism, they used a bunch of them, all working in parallel, 8 of them in the original paper. Think of it like a committee of experts all looking at the same sentence. One expert, or head, might be looking at grammar. Another might be tracking what a pronoun like it refers to. A third might be figuring out the main topic. They all do their analysis at once and then combine their insights. It's brilliant. But wait a second. This brings up a really important question. If you ditch the whole sequential thing and just look at all the words at once, like a big jumble, how on earth does the model know that the dog bit the man is different from the man bit the dog? The order is crucial, and now it's gone.
Well, the solution is just so simple and elegant: positional encodings. So before any words go into the model, a little piece of mathematical info gets added to each one that basically just stamps it with its position. You know, I'm word number 1, I'm word number 2, and so on. It's kind of like if you took a book, ripped out all the pages, shuffled them up, but then used the page numbers to put them back in the right order.
So the theory is brilliant, right? The architecture is super clever. But the only thing that really matters is, did it actually work? And, well, the results weren't just good. They were absolutely stunning.
Let's just look at the raw data from the paper. They were testing on a standard translation benchmark, measuring quality with something called a BLUE score. The best model out there at the time, the state of the art, scored a 26.3. The new transformer model came in and scored a 28.4. It didn't just inch past the record, it blew it out of the water.
Now, that jump of over 2 full points might not sound like a lot if you're not in the field, but trust me, in machine translation research, that is a massive leap. That's the kind of progress that you normally see over years of tiny improvements, and they did it in one shot with a brand new architecture.
But here's the real kicker. It wasn't just better, it was way, way more efficient. The transformer got these record-breaking results using less than 13% of the computing power it took to train the old champion. So it was better and cheaper. And this is the whole point. This was the breakthrough. The transformer wasn't a trade-off. It was a win across the board. You got higher quality, you got a design that could run on parallel processors, which made it way faster, and it cost significantly less to train. This is basically the holy grail in computer science, and it's what unlocked the ability to build the gigantic models we have today. So that brings us to the legacy of this paper, and really, it is almost impossible to overstate just how much it has changed the world of AI that we're all a part of now. The transformer architecture isn't just a part of modern AI, it is the foundation. I mean, every large language model you've ever heard of, GPT, Google's models, you name it, it's built on this. And it's not just text anymore. It's being used to generate images, to write computer code, to power search engines, and even for huge scientific breakthroughs like protein folding. It's everywhere. I want to finish on this one quote, right from the conclusion of the paper. The authors wrote, "We are excited about the future of attention-based models and plan to apply them to other tasks." Looking back at that now, from where we stand today, that has to be one of the biggest understatements in the entire history of science.
They proved that attention really was all you needed to unlock that next generation of AI. Which leaves us with a pretty fascinating question to think about. What's the next revolutionary idea? The one that we don't even know we need yet? Thanks for watching.